Now let's look at FM systems and the noise performance of FM systems. We're using the same setup as we did with the AM systems. We have the modulated signal with the added noise that is applied to a bandpass filter. The signal that comes out of the bandpass filter is the received signal. We can look at the signal power and the noise power at the input of the demodulator, and then look at the signal that comes out of the demodulator at the signal power out and the noise power out. This is the model we're using for the FM receiver. We have the FM signal plus the additional noise. And the demodulator has these three components. The first is a limiter amp. It turns out that all of the information in the FM signal is in the angle function of the FM signal. There's no information in the amplitude, so the first amplifier here establishes an output with a constant amplitude. Next is a frequency discriminator, and we will model that as a differentiating amplifier. And then that's followed by a low pass filter, and then we have the output signal on the far right hand side. Here is our expression for the FM signal: constant amplitude times a cosine. Then we have 2 pi times the carrier frequency times t. And then as the phase angle, we have a constant k times the integral of the message signal. This will give us a signal where the instantaneous frequency is proportional to the message signal. The additive noise, again, we're going to use the narrowband noise model that breaks the noise into its in-phase component and its quadrature phase component. And the received signal is simply the sum of these two signals. We have the FM signal first, and then we're adding to that the narrowband noise. The power in the received signal is found by squaring the received signal and then time averaging. So I've listed out on this next line, this is the received signal that is being squared, and it's going to have 1, 2, 3, 4, 5, 6 different terms. And then each of the terms will be time averaged. And as we've worked through these things before, all of the terms that involve the cosines will time average to 0, both the cosines and the sines. And the terms that will survive the time averaging process are going to be 1/2 AC squared plus 1/2 NC squared time averaged plus 1/2 NS squared time averaged. So this will be the signal portion is the 1/2 AC squared, so the signal power is 1/2 AC squared, and the rest of it is the noise power. Since the noise power is equally distributed across the cosine and the sine term, we can write that the noise power, as it was with the AM signals as well, was 2 times N0 times B. Now, I'm expressing in this last part of the expression, instead of using the bandwidth of the message signal in hertz, I'm expressing it in radians. So since omega is equal to 2 pi times f, that would make frequency equal to radian frequency divided by 2 pi. There's a pi. If for the bandwidth in radians, which contrary to my better judgment, it's listed here as a W because it resembles an uppercase omega, but omega is omega and W is W, and they are not the same letter. But in violation of my strict rule against this, we're expressing this bandwidth as as W in radians. That's going to be equal to the bandwidth in hertz divided by 2 pi. So so B is equal to 2 pi times W. Okay, so you can see that now we have this expression N naught times W, which is the bandwidth in radians of the message signal divided by pi. That gives us another expression for the input noise power. The limiter amp produces a signal of constant amplitude. All of the information is in the phase angle of the signal. The discriminator produces a signal given by the derivative of the angle function minus 2 pi fc, so we're subtracting out the constant from the carrier signal. So the derivative of the angle function is going to be 2 pi times fc plus k times x of t, and then we're going to subtract out the constant 2 pi fc. So this gives us the result of the discriminator, which is going to be the constant kf times x of t, and the output signal power is this signal squared and then time averaged. So the output signal power is kf squared times x squared of t time averaged. So to investigate the noise performance of this FM signal, let's find the output noise with an unmodulated carrier. So if we turn x of t down to 0. So we're taking the message signal x of t and we're going to set it equal to 0. So now the received signal is simply AC cosine 2 pi fct. That we have the angle function x of t is now equal to 0 plus the narrowband noise components. And now if we draw a phasor, we've got AC is a constant phasor along the real axis, and to this constant we are adding the random noise as a phasor on the end. So which we've broken into the in phase component and the quadrature phase component, and we have a resultant phasor, which is the sum of the signal phasor plus the noise phasors. But for frequency modulation, what we're looking at now is the angle function. So we're looking at the angle of this phasor. The magnitude of the phasor is simply the square root of the in phase components squared plus the quadrature phase components squared. So it's the square root of the real part squared plus the imaginary part squared. And the phase angle, alpha, as a function of t, is the inverse tangent of the imaginary part divided by the real part. So that's the inverse tangent of the quadrature noise component n sub s of t divided by the real part AC plus n sub c of t. If the noise is small compared to the carrier, so that NC of t is small compared to AC, so then in the denominator here we have AC plus a small number. Let's consider that to be essentially 0. Then we would be left with the inverse tangent of n sub s of t over AC. If the noise in the quadrature direction is small compared to the carrier, then this angle alpha is small. So this angle as a function of t, which is the inverse tangent of ns of t over AC, and for small angles, the angle is approximately equal to, or the inverse tangent is approximately equal to n sub s of t over AC, and we can use this as an approximation for the angle function. The output noise is going to be the time derivative of the angle function. This angle function is, as we saw on just the previous slide, is n with the subscript s of t divided by the constant AC. So when we take the derivative, we have 1 over AC as a constant, and then we're taking the derivative of the noise signal. So if if we have this expression for the time function, for the noise as a time function, its power spectral density is going to be the magnitude squared of the Fourier transform of this time function. So we're taking this time function, and I'm going to then look at the Fourier transform of the time function, and then look at the magnitude squared of the Fourier transform, and that will give the power spectral density of the noise. And it's working here using radians as the frequency variable. So the power spectral density as a function of omega is equal to the magnitude squared of the Fourier transform of the time function of the noise. 1 over AC is an amplitude constant, and that gets squared, so we have a 1 over AC squared. And now we have the Fourier transform of the derivative of the time derivative of a function. And using omega as the frequency variable, the Fourier transform of the time derivative of this function is going to be j times omega times the Fourier transform of the time function. And then all of that is magnitude squared. The magnitude squared of j is 1. And then we have an omega magnitude squared. So we bring that out, and we get now that the power spectral density of the output noise is equal to omega squared over AC squared times the power spectral times the magnitude squared of the Fourier transform of the noise, the noise time signal, which is by definition the power spectral density of the noise as a function of omega. Okay, so this gives us the power spectral density of the output noise, the noise at the output of the FM demodulator, is equal to omega squared over AC squared times the power spectral density of the input noise as a function of omega. So for Gaussian white noise, the power spectral density of the input noise is simply N naught over 2. So we've got a bandpass filter with a bandwidth of 2W, which would then is filtering this constant power spectral density. So if you look at the shape of the power spectral density for the input noise, we've got N naught over 2 as its height, and it's centered at the carrier frequency, and we're using this ideal bandpass filter, this pair of rectangles, to model that bandpass filter. The discriminator detector, this is the frequency discriminator, and the detector, it shifts this spectrum down to baseband so that when they're added together, they've got a total height of N naught, and it's got a width of 2 times W. This is the power spectral density of the noise. Now that power spectral density of the noise is then multiplied by omega squared over AC squared. And what that gives us for the power spectral density of the noise at the output of the FM detector, what that gives us is this parabolic shape to the power spectral density because of this omega squared in the numerator. So this is N naught over AC squared times omega squared. That is this parabolic shape. And what we want to find is the total noise power. So that will be given to us. The total noise power, as always, is given to us by the area underneath this shape of the power spectral density. So the total noise power out is the area underneath that power spectral density. And now, because we're working with omega instead of F as the frequency variable, the proper equation for the total power is 1 over 2 pi times the integral of the power spectral density as a function of omega d omega. See, omega is equal to 2 pi times F, so it's simply this is the power equation when we're using omega as the frequency variable instead of F. So 1 over 2 pi, and now we can integrate from 0 to w and double that value, so that's where the 2 goes. So 1 over pi, the integral from 0 to w. The power spectral density is n naught over AC squared times omega squared, and we're integrating with respect to omega. N naught and AC squared are constants. The antiderivative is 1/3 omega to the third power, and we integrate from 0 to w. So now we've got this expression for the total noise power out of the FM demodulator. This is the noise out when we had 0 message signal, so this is simply the noise power itself. N naught is the intensity of the background noise. W is the bandwidth of the filter, and it's to the third power, and then we divide it by 3 pi times AC squared. Now, the noise power at the output would go up as the bandwidth increases, but the noise power at the output goes down as the carrier amplitude AC increases. So we can make the noise output go down simply by cranking up the power in the amplitude of the FM signal. This is of a great advantage to FM. It quiets the noise. Recall the output sound power, kf squared times x squared time averaged. So we can form the signal to noise ratio at the output with the output signal power divided by the output noise power and do a bit of algebra. And we get 3 times 2 pi times AC squared times kf squared times the message signal power divided by 2 times n naught times w to the third power. So this is the signal to noise ratio at the output of an FM receiver. We can make that better by increasing the amplitude of the carrier, or by increasing this constant kf, which is related to the frequency deviation of the FM signal. So the deeper the modulation, the larger the frequency deviation, the better the noise performance. And then you could always increase the signal noise power as well. And if the detected signal, though, gets worse if we have increased background noise, and that makes sense. And it also gets worse if we increase the bandwidth of the low-pass filter, and that makes sense as well. So let's take an example where the message signal is a tone. This is tone modulation. So the message signal is a cosine at a particular amplitude with a particular frequency. So its power is 1/2 the amplitude squared. The frequency deviation would be AM times KF, and beta, the FM index of modulation, is delta omega divided by omega m. And omega m is equal to uppercase W. So using those in the previous expression, we get a signal to noise ratio 3 pi AC squared beta squared, that's the FM index of modulation, divided by 2 times n naught times omega m. And the signal to noise ratio at the input, we have the signal power divided by the noise power. Turns out to be pi AC squared over 2 n naught times omega m. So comparing the signal to noise ratio at the output to the signal to noise ratio at the input, and everything cancels, that leaves us 3 times beta squared. So the signal to noise ratio at the output is equal to 3 beta squared times the signal to noise ratio at the input. So for the detector to improve the signal to noise ratio, then 3 times beta squared must be greater than or equal to 1. So that would make beta greater than or equal to the square root of 1/3, which is 0.577, which is, if you remember weeks ago, this is essentially the distinction between narrowband FM, and wideband FM. Narrowband FM has a small value of beta certainly less than 0.577, and wideband FM has a beta greater than 0.577. So in order for the detector to improve the signal-to-noise ratio, we must use wideband FM. Calling the signal-to-noise ratio, the signal power at the input is AC, 1/2 AC squared. So the signal-to-noise ratio at the output of the FM detector, we can take this AC squared and this 2 and replace that by signal power N. So we get 3 pi beta squared signal N divided by signal power N divided by N naught times omega N M. So comparing the FM signal-to-noise ratio with the baseband signal-to-noise ratio, after everything cancels, we get, again, 3 beta squared as the comparison. For conventional amplitude modulation, signal-to-noise ratio was AC squared X squared time average divided by NC squared time averaged. For tone modulated wideband noise power, that would be the signal-to-noise ratio pi AC M squared divided by 2 N naught omega M at best for M equals 1. This is the best signal-to-noise ratio one can achieve with an AM signal. Now I want to compare that with an FM signal. The signal-to-noise ratio at the output of the FM detector is equal to 3 times beta squared times the signal-to-noise ratio at the output of the AM detector. So FM signals are better by a factor of 3 times beta squared. Again, you've got to have wideband FM before the FM signal is has better performance than the AM signal. And the price you pay for this improved signal-to-noise ratio is more bandwidth required for the modulated signal. So for FM to perform better than AM, 3 beta squared must be greater than or equal to 1. That makes beta greater than or equal to 0.577, which is the line between narrowband FM and wideband FM.